Greetings, everyone. Thanks for this opportunity for participating in this second VICAFAST. My topic is biofuels from water hyacinth via hydrothermal liquefaction process. What is hydrothermal process? It is a process in which temperature and pressure makes a key role in converting wet organic materials into syngas, biocrude, biochar. There are three types of hydrothermal process in which hydrothermal carbonization in which char is more yield, and hydrothermal liquefaction process in which biocrude is a high yield product, and hydrothermal gasification whereas syngas will be the higher yield. In all these three process, biochar, bio-oil or biocrude and syngas will be the products. And my research is on hydrothermal liquefaction process of utilizing water hyacinth into biofuels. Hydrothermal liquefaction involves direct liquefaction of biomass with the presence of water and perhaps some catalyst to directly convert biomass into liquid oil with a reacting temperature of lower than 400 degrees centigrade. It takes place the temperature. My process is 280 to 370 degrees centigrade without adding any catalyst with a pressure 10 to 25 megapascal. The main products is a backroot with a relatively high heating value, char and water soluble substances and gases. So phase diagram. What happens in hydrothermal liquefaction process? It happens where the critical in the phase where the liquid is converted into vapor stage. In that cases, what happens? All these cellulose, protein, lipids, lignin content of starch of plant biomaterials or any wet waste is converted into phenols, sugars, amino acids, fatty acids, and hydrocarbons under low temperature and high pressure. That is, high pressure is nothing but more than, it's not more than 20 megapascal, it is less than 20 megapascal at the temperature of 280 degree centigrade. So why I have chosen water hyacinth? Because it is a shocking material in water bodies in the country and causing serious ecological and economical process. It removes invasive species has proved futile since they come back almost immediately. Not even a gap of like one or 2 weeks. It grows very fastly, and mainly now the traditional water hyacinths are being cleared by and dumped as garbage with average cost of rupees 25,000 per tank. So this has to be overcome. So what we are going to do with the cleared water hyacinth? It can be converted into biofuels. So why water hyacinth as a main feedstock? Because it is a moisture content of 9.54 that is not on the harvested stage. So I have chosen the water hyacinth at 9.54 percentage. Even at the range of like 90 percentage, water hyacinth can also be used here in this hydrothermal process. Bulk density, porosity, particle density has been found out, and volatile matter, ash, fixed carbon content, carbon, hydrogen, oxygen, and nitrogen content, cellulose, hemicellulose, lignin, and calorific value. So these shows that it is a good raw material for converting into biofuels. So this is a reactor, 5-liter capacity HTL reactor, in which we have an heating coil so that the temperature is maintained and pressure regulator. So once on the reactor a temperature and the thing is attained, after residence time the valve is opened and it is collected in the condenser, which is where the phase changed material is condensed into a biocrude, and this biocrude can be taken out and uh, distilled for further products, and char is collected and non-condensable gases is also collected and characterized. So these are all the products obtained from this process. Condensate, which is consist of biocrude and then aqueous phase, char, which is of wet stage, and then dried char material is there, which can be used as a amendment in the soil or as a briquetted or pelletized as a fuel. So these are the optimized conditions which I work on. The effect of reaction parameters, which is where I varied temperature, biomass water ratio, residence time on product conversion and distribution. The high solvent to mass ratio reduced the amount of leftover residues due to increase in solvation for biomass components. It was observed that at very low biomass and solvent ratios, the amount of liquid oils decreased comprehensively. So the optimum temperature obtained for this water ion conversion and to yield higher by oil yield or by crude yield was found to be to 80 degrees centigrade. And thermal studies also, the variation of 250 to 80 300 degrees centigrade with residence time variations 15, 30 and 45 minutes. So the effect of biomass and water ratio, that is like 1 is to 3, 1 is to 6, 1 is to 9 and 1 is to 12 was also studied and optimized. In the table, we can see that backroot of 16% has been the maximum yield, even though there are like 18 percentage at 300. When we go with energy efficiency, this found to be highest because of this also confirmed with the RSM box and design, and this is an optimized design. Readings of to which by water hyacinth can be used as an biofuels. So the bicrude which is obtained from this process has been characterized in GC chromatograph and then FTR spectra. So in GCMS analysis of bicrude, it found that the maximum of terpenine, dimethyl benzyl alcohol, cyprol, cyclohexene, acetylcholine, etc. Are being found in these products. And this FTI analysis also confirmed that the bandwidth of 2875 to 3000 degrees centimeter, so which confirms that CH stretching bonds, and wavelength of 1700 per centimeter confirms the C double bond O functional groups, and the wavelength 1300 to 1500 per centimeter confirms that benzene ring stretching vibrations, and this lower peaks like in the around of 1100 to 1270 per centimeter are said to be a alcohol stretching carbon oxygen bonds. So these confirm that this biocrot can be estimated, can be utilized or can be recovered uh, to extract phenolic compounds, acid form compounds, and esters. So this can be a biofuel for in chemical industries. That is biochemical, or we can say it is an organic material, eco-friendly material for any chemical synthesis like phenolics, acids, and esters. Even petroleum compounds can also be extracted from this biocrude. The optimized reaction condition is to 80 degrees centigrade, time 15 minutes, and biomass water ratio 1 is to 6, which yields about 16% of biocrude, 11% of non-condensable gas, 16% of residue with 84% conversion. So it also confirmed that these 11% of non-condensable gases can also be used as a thermal fuel. That is, it can be burned for heating the biomass in higher scale production. The energy consumption ratio for HTL is found to be 0.82, which is very lesser than the pyrolysis process, in which in pyrolysis it leads to 1.5 to 2.2 energy consumption ratio. So again, GCMS and FTI analysis of bicrude confirm that it contains a complex mixture of aromatics and aliphatic derivatives. So this is a good raw material to be converted into an biofuel. Uh, Even if we have catalyst, the bicrude yield can be enhanced. Even though without adding any catalyst also, it yields a good amount of biocrude, in which we can obtain eco-friendly biofuels and biochemicals. Thank you. And I acknowledge ICR CRP for funding this project and Department of Renewable Energy Engineering to allowed to carry out this research. Thank you.